Linear functions. Let's start by looking at linear functions analytically. A linear function can be written in the form y equals mx plus b or f of x equals mx plus b, with slope, the value of m, the number that's being multiplied by the variable x, and y-intercept, the coordinate point 0, b. So the constant value in the equation is the y-intercept. This is called slope-intercept form of a line for the obvious reason that we can easily identify the slope and the y-intercept. In this example, we want to determine which of the following functions are linear, and we're going to go ahead and circle them. So in this first example, I have 2x minus 3y equals 36. Remember we just said that a linear function can be written in the form y equals mx plus b. So let's take this equation. I'm going to do my scratch work on the side here. 2x minus 3y equals 36, and try to solve it for y and see if we can write it in that y equals mx plus b form. So I'm going to subtract the 2x to the other side. So I have negative 3y equals 36 minus 2x. And then I'm going to divide both sides by a negative 3. So the negative 3's are going to cancel and give me a 1. Y is equal to negative 12 plus 2/3 times x. So the negatives here will cancel and give me a positive. And because addition is commutative, I can switch the places of these two terms to give me 2/3 x minus 12. So I am able to write this equation in mx plus b form. So this is a linear function. Now moving over here to the right, I have y equals 2x squared plus 3. So since the variable here x is squared, this is not a linear function. And that's going to bring me back to the first example for a second. I didn't really have to do all of the work over here and write it in y equals mx plus b form to convince myself that it's linear. In the original equation over here, if I'm able to recognize that x is raised to the first power and y is raised to the first power, then I know that I have a linear function. So here the problem is that x is squared. Now moving on, here I have y equals 2. So this is a linear function as well, and if we want to convince ourselves by writing it as y equals mx plus b, I can think about this as y equals 0x plus 2. So here, the slope is simply 0, and the y-intercept is 2. Now this is a perfectly horizontal line, which is why the slope is 0. So this is a linear function. And then finally, f of x equals 4 minus x over 2. So first I want to think about this as 4 minus 1/2 x. So I can think about this as 1/2 times x. And then here, I can switch the terms by the commutative property. So negative 1/2 x plus 4. And then I can really see that mx plus b taking shape. So this is also a linear function. Now let's review some formulas that deal with linear functions. First, let's look at the slope between 2 points, x1, y1, and x2, y2. To find the slope, m, that's going to equal in the numerator, y2 minus y1, all over in the denominator, x2 minus x1. And then let's look at the forms of a line. We just reviewed slope-intercept form, which is y equals mx plus b. And typically that is known for being good for graphing. So we can easily identify the y-intercept 0b and apply the slope m to get a second point on the line. Then we have point-slope form, and that looks like y minus y1 equals m times the quantity x minus x1. So just as the name suggests, we need a point and a slope for this form of a line, the point x1, y1, and the slope m. And we typically use point-slope form for writing an equation of a line. Finally, we have standard form, which is a little less common. It looks like ax plus by equals c, where a, b, and c are constants, just some numbers. And one of the benefits of standard form is it's good for finding intercepts. So for example, if I wanted to find the y-intercept, I let x equal 0. That means this whole first term is 0, and to solve for y, I can simply divide by b. So it's good for finding intercepts mentally. In this example, we want to write an equation of the line given the following information. In part A, we have this line that passes through the point 3, -2 with slope 4. So I've been given a point, x1, y1, and a slope, m. Now anytime we see the instructions write an equation of a line, we would typically think about point-slope form of a line. In general, that's y minus y1 equals m times the quantity x minus x1. So we have all the information we need to substitute into this form of a line. We're going to substitute in our x1, y1, and our m. So let's go ahead and do that. I have y minus -2 equals positive 4 times the quantity x minus 3. Now here I can clean this up a little bit. Y minus -2 is y plus 2 equals 4 times the quantity x minus 3. So here, this is an equation of a line. It's written in point-slope form. Since the instructions don't specify how to leave your answer, this is a perfectly fine way to leave your answer. Sometimes students really want to write their answer, though, in slope-intercept form. And that's fine. Let's review writing our answer in slope-intercept form, especially because the instructions might ask for that form. So I'm going to go ahead and bring my work up here and write y equals, y plus 2 equals 4x minus 12. So I'm going to distribute the 4 in, and ultimately I'm solving for y. So I'm going to subtract the 2 to the other side. Y equals 4x minus 14. So this is the answer in slope-intercept form. For this problem, either one is fine, but there might be a set of instructions which ask you to leave your answer in a particular form. Now we want to write an equation of a line given that the following information, that here the line passes through the points 4, 1 and -2, 7. So this time I've been given 2 points, an x1, y1 and an x2, y2. Well, again, anytime you see write an equation of a line, we would typically think about point-slope form of a line. Y minus y1 equals m times the quantity x minus x1. So this time we have an x1, y1. We have a coordinate point. In fact, we have 2. But we're missing the slope m. At least we're not explicitly given the slope m. But because we're given 2 points, we can find the slope m. So to find the slope between 2 points, we use the formula m equals y2 minus y1. So 7 minus 1 is in the numerator over x2 minus x1. -2 minus 4 in the denominator. So we get 6 over -6. So I have slope -1. Now I can simply substitute my slope in to point-slope form of a line, and I can choose either coordinate point. So I'm going to go ahead and start by saying y minus 1 equals -1, but I'm just going to leave it as a negative, times the quantity x minus 4. So here, this is a perfectly acceptable answer. I'm going to write a couple different versions. I'm also going to put y minus 7 equals -1 times x plus 2. So we can use either one of the points, and that's fine. And these are actually the exact same answer. So to show that, what we could do is we could solve for y to get that slope-intercept form. So here I'm going to go ahead and just do that mentally and think about this is going to end up being negative x and then plus 4. So we're going to have negative x. And then when I add the 1 to the other side, it's going to be minus x plus 5. And again, we can just do some quick mental math here. This would be a negative x and then minus 2, but when I add the 7 to the other side, it's still going to give me plus 5. So all of these are equivalent answers. These all represent the same line. And in this last one, we're still going to write an equation of the line given the following, that our line passes through negative 3, 4 with slope 0. So this time we're given a coordinate point, x1, y1, and we're given our slope is m equals 0. So we can jump straight to point slope form of a line, y minus y1 equals m times the quantity x minus x1. And we'll start to substitute in y minus 4 equals 0 times the quantity x plus 3. So notice on the right hand side, 0 times this quantity is just going to give me 0. So I have y minus 4 equals 0, or y equals 4. So here my equation of the line is y equals 4. And that's because this is a horizontal line, which we could have established when we saw that this line had a slope of 0. If a line has a slope of 0, it's perfectly horizontal. And horizontal lines have the form y equals. So we could have skipped all of this work and just recognized that a line with slope 0 is of the form y equals a number, and if this line passes through the point negative 3, 4, then the equation must be y equals the y value 4. Now let's move on and think about linear functions numerically. A linear function can be represented in tabular form. The relationship between the x values and the y values must be a constant sum or difference to be a linear function. So let's take a look at an example. Let's determine if the function is linear or non-linear. If it is linear, find the slope. So here we have the first example. So we have this table of values. X goes 0, 1, 2, 3, 4. And the y values go 13, 10, 7, 4, 1. So we need to make sure the relationship between the x values is a constant sum or difference, and the relationship between the y values is a constant sum or difference. So here, going from each x value to the next, I'm always adding 1 each time. And then when I move along the y values, to get from 13 to 10, I'm subtracting 3, 10 to 7, subtracting 3, 7 to 4, and 4 to 1, I'm subtracting 3. So I have this constant difference every time, and here I have a constant sum every time. So this is an example of a linear function given in tabular form or given numerically. So here we do have a linear function. And then the second part is, well, if it's linear, then let's go ahead and find the slope. Well, the slope, m, is going to be the change in y values. So remember, we need two coordinate points, x1, y1, and x2, y2. And remember what we do, we subtract the y values in the numerator and then subtract the x values in the denominator. So here, we found that the difference in the numerator was negative 3 every time, and the difference between the x values, which would go in the denominator, is 1 every time. So the slope is simply negative 3. So in thinking about whether or not we have a linear function, we can identify the slope by thinking about the change in the y values over the change in the x values. So now let's go ahead and look at this second example here. Let's look at the change in those x values. So here, to get from negative 3 to negative 1, we're adding 2. Negative 1 to 1, we're adding 2. 1 to 3, we're adding 2. 3 to 5, we're adding 2. So we have a constant sum in the the x values. And then let's look at the y values, or the f of x values, the outputs. Here, we're adding 0 every time. We are adding 0 every time. Or in other words, there is no change in the y values. But it's still a constant, right? It's not changing anywhere. So this is a linear function. And when I go to analyze the slope, it's going to be the change in the y values, which is none, 0, over the change in the x values, 2. 0 divided by 2 is 0. So this represents a line with slope 0, or a horizontal line. And that should make sense, because what we're saying is that it doesn't matter what x value you plug in, you're always going to get out 8. So it's like a horizontal line across the board, because everywhere it's just y equals 8, y equals 8, y equals 8, all the way across, giving you a horizontal line which has a slope of 0. So if there were a table where to get from one value to the next, maybe you're adding 2, and then to get from one value to the next you're adding 4, and then you're adding 2 again, and then you're adding 3. If the values are not constantly the same, constant sum or constant difference all the way down, then I don't have a linear function represented by that table. Now let's talk about linear functions graphically. So we went over them analytically, numerically, and now graphically. So the graph of a linear function, y equals mx plus b, is a line. And remember that 2 points define a line. So in this example, we're asked to graph each of the following. Graph y equals negative x over 3 plus 4. So let's go ahead and think about this as negative 1/3 x plus 4. So I'm going to write that above it where I have some space. Negative 1/3 x plus 4. So I can just separate the m and the b value. So we said earlier that this slope-intercept form of a line is good for graphing. And the reason is because I can automatically plot the y-intercept. So we know that 0, 4 is the y-intercept. So I'm going to plot that 1 point. And then what I can do is apply the slope. So negative 1/3 is the slope. And I'm going to go ahead and sort of break that down over here. So I can think about negative 1/3 as either negative 1 over 3 or 1 over negative 3. So I can think about the negative with the numerator or denominator. If I think about the negative with the numerator, then the slope is a little set of instructions that's telling me to go down 1 and right 3. So if you remember, slope is rise over run, but since it's negative, it's telling me to fall or go down, and then run right or left. Since it's positive, run to the right. So from this coordinate point, I'm going to go down 1 unit and then right 3 units. So that's going to get me to the point 3, 3. So now I have 2 points on my line. And that's all I need. I only need 2 points to define a line. So let me see if I can get this nice looking. There we go. So this is my linear function. Now remember, lines go on forever, and we can put the arrows at the end to just remind and be just extra thorough about reminding ourselves that the line does keep going on and on forever. Now if we would have chosen to think about the negative with the denominator instead, so 1 over negative 3, then this set of instructions says go up 1, left 3. So from the y-intercept, I would have gone up 1 unit and then left 1, 2, 3 units, getting me to negative 3, 5, which notice is still a point on the line. So we can graph a line by graphing any 2 points on the line. So it didn't matter which way we chose to interpret the slope, with the negative in the numerator or the negative in the denominator. Looking at part B, I have f of x equals negative 2 plus 3x. So here, I want to just be careful with correctly identifying which is the slope and which is the y-intercept. The slope is the number that's in front of the variable x, and then the constant is the y-intercept. So my y-intercept value, whoops, that's not a highlighter, is negative 2, and then my slope is positive 3. So I'm going to go ahead and plot my y-intercept. Again, that's on the y-axis up and down. So I'm going to plot it at -2. And then to find a second point, I want to apply the slope. So the slope here is m equals 3. I want to think about it as a rise over run, so I'm going to write it as 3 over 1. So since both of these are positive, I can think about it as up 3 and then right 1. So I'm going to go from the y-intercept at -2 up 3 units, 1, 2, 3, and then to the right 1 unit, landing me to the point 1, 1. And then I'm going to go ahead and connect those 2 points and then put the arrows just to be super thorough about reminding myself that lines go on forever. And this is my linear function, -2 plus 3x, or 3x minus 2. We could have chosen, although this is a little bit less common, but we could have chosen to think about this 3 over 1 as -3 over -1, because 2 negatives would cancel and give me a positive. And then we could have thought about this as down 3, left 1. So from the y-intercept -2, I could have gone down 1, 2, 3 units, left 1 unit, and that would have gotten me to -1, -5, which you can see is another point on the line. Now finally, I have the line y equals -3, and we really just want to know at this point, and remember that if you have y equals a number, that's simply a horizontal line. So y equals -3 would be this perfectly horizontal line along -3. Now let's take a look at the idea of a linear function being increasing, decreasing, or constant. If the slope is positive, we have an increasing function. If the slope is negative, we have a decreasing function. If the slope is 0, we have a constant function. So here our increasing function, as I move from left to right, the y values are getting bigger. On my decreasing function, from left to right, my y values are getting smaller. And here, as I move from left to right, my y values are not changing, they are constant. And I have a slope that is 0. In this example, I want to identify, is each function increasing, decreasing, or constant? Identify its slope and write an equation for the line. So first, looking at this left graph, as I move from left to right, I can see that my y values are falling. It's like I'm walking down a hill. So it's a decreasing function that I'm looking at. So we'll start with that. And the second part of the question is, what is its slope? And then write an equation for the line. So to find the slope, I need 2 points on the line. And when I choose these 2 points, I want to make sure and pick points that fall on integer values. I don't ever want to approximate a point value. So in other words, I'm going to go ahead and pick this point that I can clearly see is at -3, 4. And I'm also going to pick this y-intercept value at 0, 3. I pass through 0, 3. So I'm going to label those. I have -3, 4. I have 0, 3. I could also have chosen, let's see, 3, 2. That's another point. So I'll just emphasize that as well, the point 3, 2. So I want to pick 2 points that fall on nice integer values. So to find the slope, because I've written out the coordinate points, I could use the slope formula. y2 minus y1 over x2 minus x1. But we want to just be able to identify the slope by looking at 2 points specifically and figuring out, well, what is the set of instructions that takes me from one point to the other point. So let's say I start at -3, 4. How do I get to 0, 3? Well, I'm going to travel down 1 unit. So I'm going to travel down 1. And then I'm going to travel to the right, to the right 3 units. And it didn't matter if I had picked this point here, 0, 3, and how did I get to 3, 2? I'm going to go down 1, right 3 again. So now to interpret this set of instructions and turn it into a numerical slope, remember that we think about slope as rise over run. Well, the rise in this case is a fall. So since I'm going down, we're going to say -1 is the numerator. And because I'm going to the right, I'm going to have a positive 3. So my slope is negative 1/3. Now the next part is write an equation for the line. Now since I have the slope, and I have a point on the line, I can use point-slope form of a line. So I actually have 3 different points on the line, but I can use point-slope form of a line, so that is one option. So I'm going to go ahead and write that out. So I do have the option to say y minus 4, let's say, I'm going to pick this point, y minus y1 equals negative 1/3 x plus 3. So this is an equation of the line, but because I have the y-intercept value, in addition to the slope, I could have gone straight to writing the slope-intercept version of the equation of the line. So I could have went to y equals mx plus b, because my slope, is negative 1/3 x plus the y-intercept value is positive 3. So negative 1/3 x plus 3. Let's go ahead and take a look at the second example over here. The first thing I want to recognize is that this is an increasing function. So as I move from left to right, my y values are going up. It's like I'm going up a hill. So I have an increasing function. Then I want to identify the slope of this line. So I want to pick 2 points on this line that pass through those integer values. So I can see one of the points I have is just like last time, the y-intercept, and it's a nice y-intercept. It's an integer value. So 0, negative 1 down here. And then I'm going to go ahead and move along the line and try to find, well, where do I fall or cross another pair of integer values for x and y? Well, this is slightly off, right? I don't have a point that goes through 1, 0. So I want to just keep following it, and I see that I do have one at 5, 3. So I can see that I pass through 5, 3. So now that I have 2 points on the line, which is all I need, I want to think about that set of instructions. How do I get from one point to the other point? So I'm going to pick one point and describe how many units I move up. So I go 1, 2, 3, 4 units up. So up 4, and then how far do I head to the right? Well, I go 5 units to the right. 1, 2, 3, 4, 5. So I go right 5 units. So my slope is then m equals positive 4 over positive 5. So because I'm going up, the numerator is positive. Because I'm going to the right, the denominator is positive. So we can see the slope is a positive value because I have an increasing line or function. Over here, my slope was negative because I had a decreasing function. And now I want to write the equation of the line. Well, here, because I have the y-intercept again, I can go ahead and jump straight to slope-intercept form of a line. I could say y equals 4/5 x minus 1. Just right away, 4/5 is the slope, the y-intercept is negative 1, so plugging it into mx plus b. In this next example, I'm given the graph of a linear function, and the name of that linear function is g of x. And in parts A through E, I'm asked to solve some linear equations and linear inequalities. Now let's just take a second to think about what the answers would look like if we were to solve this analytically. So here, we aren't given the equation of the line, but let's pretend that we were given the equation of the line. So let's just say we were given, let's just say we were given that g of x happens to equal negative 2x plus 30. So if you're solving g of x equals 60, then you're going to set the equation negative 2x plus 30 equal to 60. And then what are you solving for? Well, you're solving for the missing variable. What's missing is x. So you're going to subtract the 30 to the other side. 2x equals 30, divide by negative 2. We get the x value, x equals negative 15. Right, so that is my solution. All right, so the bottom line is, I wanted to review this because what we're solving for is an x value. So I want us to just go ahead and keep that in mind. The same thing would apply when we're solving these inequalities. We're solving for x values. All right, part A here, solve. When does g of x equal 60? So at what x value does the line equal 60? So over here, I have this point marked at negative 15, 60. So the x value is negative 15 that corresponds to the y value, or the g of x value, 60. So my solution here is just the x value, negative 15. And when we solve, we put our answers in curly braces. It's a solution set. All right, another way to think about this is we can think about this as solve when does the g of x line, so g of x is a linear function, when does that equal the function 60? Well, the function 60, y equals 60, is a horizontal line at 60. So it's like, where does the horizontal line, y equals 60, equal, right, or intersect the g of x function? So they intersect at the x value, right, my answer is an x value, x equals negative 15. That's another way to think about it. So again, the answer has to be, what's the x value where g of x equals 60, the y value equals 60? Let's go ahead and take a look at part B. Solve, when does g of x equal 0? So when does this function, this linear function, equal 0? Remember the y value, g of x is y. So at what x value does the y value equal 0? Well, the y value is 0 along the x-axis, so that happens at the x value, positive 15. So my solution here is positive 15. Now, parts C through E are inequalities, so my answers are going to be intervals. Solve, when is g of x greater than 20? Solve, when is the g of x function greater than 20? So where are the y values greater than 20? So what I'm going to go ahead and do is realize that at 520, that's one location where the y value is 20. I want to know all the x values that will give me a y value that's bigger than 20. So I'm going to highlight that region. That region is going to be this top part of the line over here. So another way to think about it, again, when I see these individual numbers on, in this case, the right-hand side, I can think about those as their own horizontal lines. So let's draw a horizontal line at y equals 20 for a second, because then this problem ends up translating to, well, where is g of x above 20? So where is this line above this line? So that's why I've highlighted this yellow part right here. So the g of x line is above 20 over here. Now, how would I describe over here? How do I describe these x values? So along the x-axis, we would say all the way from negative infinity to 5, where they intersect. So as an interval, we're saying negative infinity all the way to 5, not including 5, right? Not including 5, because that's where they're equal. I want to know where is g of x above 20? Where are the y values above 20, not equal to 20? So now let's take a look at part D. Let's erase this. Solve, where is g of x less than or equal to 60? So where are the y values less than or equal to 60? So I can draw that line at y equals 60 and ask, where is g of x below, less than, or equal to that line? So here's where g of x is directly below, right, thinking vertically up and down, where am I directly below this line? And then also right at the intersection point, less than or equal to. So how do I describe this interval of values? As x values. So starting at x equals negative 15, so we're going to go ahead and say from negative 15 all the way to infinity, including negative 15. All right, and then the last one, solve, where is 0 less than g of x less than or equal to 60? Or another way to think about it is, where is g of x trapped between 0 and 60? So on what x values are the y values of the line trapped between 0 and 60? So I'm going to go ahead and erase what we have so far. Whoops, I could have left that line. So I'm going to keep a line right here at y equals 60, and I'm going to emphasize the x-axis because that's y equals 0. And we want to know, well, where is g of x, on what x values is g of x trapped between 0 and 60? So that's this region here. But I want to know, let's see, g of x has to be strictly greater than 0, so I don't want to include this x value here, but I want to know, where is g of x less than or equal to 60? So I am going to include this x value up here. So how do I describe this interval of values? So it starts at -15. We always go smallest to biggest. So on the x-axis, we're looking at -15. We do want to include -15 to +15, but we don't want to include +15 because I wanted to know, where is g of x strictly greater than 0, not where am I greater than or equal to 0. So whenever we're solving these equations or inequalities, we're solving for x values. So we could be extremely clear about that by putting that these are x values. So the solution is, in A and B, the specific x value, in C, D, and E, the x values within these intervals. In this example, we're given the graphs of f of x and g of x. Both are linear functions. We're basically extending the ideas from the previous example. Now we're solving an equation and some inequalities, but with two different linear functions involved. So when we're solving for x values. So solve, when does f of x equal g of x? For what x values does the f of x function equal the g of x function? So we're focusing on their point of intersection, but specifically at what x value are they equal? So that x value is +3. So just this one individual number at +3 is when f of x is equal to g of x. In part B, solve, when is f of x less than g of x? So when we're looking at the graphs, we want to think about the less than symbol as below, right? So we're thinking about, when is f of x, the red graph, below g of x, the blue graph? So basically, where is red below blue? So that's going to happen on the left side of the graph. On the left side of the graph is when f of x is below g of x. Now, how do I answer the question? I describe that as an x interval of values. So from -infinity, because we assume these lines go on forever because they don't have fixed points at the end. They don't need the arrows. So we have -infinity all the way up until 3, but not including 3, because right at 3 they're equal. I don't have f of x below g of x at 3. So we're going to go ahead and describe this interval as x values from -infinity to 3, open. And then part C, solve, when is g of x greater than 2? So on what interval is g of x greater than 2? So we want to think about 2 as its own function. It's the horizontal line at y equals 2. So I'm going to go ahead and draw a horizontal line at y equals 2. So in other words, like here we have two lines, f of x and g of x, and we also have this third line now, just y equals 2. I mean, we could have called it h of x if we want to, but we're just thinking about this third line now, y equals 2. So this question is, where is g of x above this line 2? Right, where is g of x above 2? So g of x is the blue function. So where is blue above my green function? So that's going to happen over here. Green is above blue, the left side of the graph again. So it's actually the same interval as the last answer, from -infinity to 3. not including 3. So x values are between negative infinity to 3, not including 3. So the other thing to remember when you're solving equations and inequalities is that when you find a solution, you should always check your work. Now, when you do it algebraically, you take that x value and you plug it into the equation or inequality, make sure the statement's still true. So here, if I picked a value in this interval, so what's a number between negative infinity and 3? So let's say 0. So what we're saying is that at x equals 0, so right here at x equals 0, is the f of x graph, the red graph, it's down here at negative 2, is negative 2 less than what's going on at the g of x graph at 0? Well, the g of x graph is up here at 3. So yeah, negative 2 is less than 3 when we plug in x equals 0. So we still have the idea of checking our solution set. Finally, let's take a look at some applications of linear functions. Given a linear function, y equals mx plus b, the average rate of change is the slope. So in this example, given each linear function, find its average rate of change and determine whether it's increasing, decreasing, or constant over its domain. We're just finding the slope. Now, in part A, f of x equals 8 minus 2x. So the average rate of change, here's the approximation, AROC, is just the slope. The slope in slope-intercept form is the number multiplied by x. So the average rate of change is negative 2. And because that's a negative value, we know that our linear function is decreasing. In part B, h of z is equal to 7. Or let's remember this would be 0 times z plus 7, indicating that our average rate of change, or slope, is 0. This is just a horizontal line. And so that means that I have a constant linear function. In part in part C, g of t is 1/2 t plus 2. So my average rate of change is the slope positive 1/2, the number that is multiplied by the variable, in this case t. And since this is a positive number, we know this linear function is increasing. In this example, we're going to go ahead and need to build a linear model. So in general, I just want to go ahead and write what a linear model would look like sort of generically. So my linear model, let's call it f of t, is going to look like the average rate of change times t plus the initial value. So you should notice that it sort of models the y equals mx plus b look, and we just said that the slope m was the average rate of change, and that's going to get multiplied by the variable. In this case, I've made it t because our real-world examples are usually a function of time. And then plus this initial or starting value. And we call it an initial value because if time is 0, so initially time is 0, then this first term will disappear and all I'll have left is this quantity. So this is the initial value. So here we're going to take a look at this example. So we have for calls from the US to Germany on a certain phone plan, there's a flat rate of $5 per month, and calls are 26 cents per minute. Write a linear model C to represent the monthly phone bill in terms of X, the number of minutes used. So we're going to write a linear model. So up here, this is going to be our generic linear model. So we need to fill in our average rate of change value and our initial value. We're not going to call it f of t though, we are going to call it c of x. So c of x is going to be, let's think about what our average rate of change is versus our initial value. So in this initial statement that we're given, there's a flat rate of $5 per month, and then calls are 26 cents per minute. So the initial value that you're going to be charged, no matter what, is this flat rate of $5. So that's going to be your initial value. You're going to get charged that no matter how many minutes you're on the phone. But then you're going to get charged 26 cents per each minute. And X is the number of minutes. So that's why we're going to multiply 0.26 times X. 0.26 is my average rate of change. So I'm going to label this. This is my average rate of change plus 5. This is my initial value. All right, so this is what I'm going to get charged because C is the bill. So this is my initial bill no matter what, plus the amount per minute times the number of minutes. So remember that X is in minutes. So I'm going to label that as well. Now the benefit of creating a linear model here is that we want to use it to answer the other parts of the question. So what is the cost if you talk on the phone for X equals 50 minutes? This is kind of a giveaway here saying X equals 50 minutes because it's clear that we're just going to plug 50 into X. But keep in mind, this X equals doesn't have to be given. So if you were just asked, what is the cost if you talk on the phone for 50 minutes, we'd have to know to plug 50 into X because X is in minutes. So C of 50 is going to be 0.26 times 50 plus 5. 0.26 times 50 is 13 plus 5 is 18. And then let's keep in mind this is a cost. So what came out has a units of dollars, $18. Let's take a look at part C of the same question. Suppose that your monthly bill is $21.64. How many minutes did you use the phone? So we're working with the same model, C of X equals 0.26x plus 5. But this time we're given that the bill, the cost, the left side of the equation is $21.64. So that has to equal the model 20.26x plus 5, and we're solving for minutes. How many minutes did we use the phone? We're solving for X. We'll subtract 5 to the other side, so we'll get $16.64 equals 0.26x. We'll divide both sides by that 26 cents and get the nice number 64. And then the units are going to be in minutes. How many minutes did you use that phone? 64 minutes. In part D, suppose that you budget yourself $50 per month for the phone. What is the maximum number of minutes you can talk? So again, this time we're given a dollar amount. So we're going to have to substitute that dollar amount, $50, into the left side of the equation and solve for X. So subtract the 5 to the other side, 45 equals 0.26x. We'll divide both sides by that 0.26, and we get X equals about 173.07. So the question is, what is the maximum number of minutes you can talk? So here, no matter what the part is after the decimal, I'm still going to round this number down because I want to know what's the most number of minutes I can talk. So even if this was 173.97, I can't talk 174 minutes because that will automatically put me over my $50 per month limit. So no matter what comes after the decimal here, we're not going to follow the standard rounding rules because we want to know the most number of minutes I can talk. So that's going to be 173 minutes of talk time. Part E, the last part, asks what is the implied domain of C if there are 30 days in the month? So remember that domain is asking us about the type of X values or the type of inputs for this particular function that make the output make sense. So what type of values can we substitute into this function? Now in general, for a linear function without any context, so if I just have some linear function and it doesn't represent, let's say, cost or anything, it's just a linear function, the domain is all real numbers. But this cost function has context. It represents something specific. So here, what type of values we are allowed to plug in are minutes. That's the units are in minutes. And so what's the least amount of minutes I can possibly plug into this function? Well, I could talk for 0 minutes. So I can't talk for negative minutes. So that's, another reason why the domain isn't negative infinity to infinity, all real numbers. The least amount of minutes I can talk is 0. So if I start to think about the implied domain, I'm going to put a bracket 0. I could just get charged $5. And then I want to think about, okay, well, what's the most amount of minutes I can talk in a month? Well, there is a most amount of minutes. If I were on the phone every single minute of every hour of every day in the month. So in other words, if I were on the phone for every minute of every hour times 24 hours times 30 days in the month. So it turns out that that number is 43,200. So that's the biggest number I can substitute into this particular function. So the domain is 0 to 43,200. And I can plug in that number, so I would use a closed bracket around that interval.